Hi, in today's video we're going to be talking about alkene and alkyne reduction. So alkenes and alkynes are reduced in the presence of palladium on carbon with hydrogen gas, and you notice that the two hydrogen atoms of hydrogen gas end up syn, so they are on the same side of this molecule. Again, if we keep track of the atoms that were there, they end up both getting pushed up in this case. It's important to note that you would wind up with this particular molecule with a mixture of both enantiomers, so both faces are able to be reacted with this hydrogen gas. So in this case, they approach from the bottom side of the molecule. In this case, they approach from the top side of the molecule. But if the molecule already has one face that is sterically blocked, in this case, there's this isopropyl, then in that case, only the bottom face would be expected to react because this top face is being blocked by this isopropyl group. And so the way the mechanism works is that the hydrogen gets absorbed onto the palladium surface. This is a heterogeneous catalyst, meaning there are little particles of this palladium on carbon floating around solution. And the electrons of the double bond, or the double bonds, this is shown here with its orbitals, approach, again, from one face, and only one face, approach kind of in a flat fashion down onto the surface, which has these hydrogen atoms attached. I want to point out that in part because of this mechanism, you never observe the anti-product for this. So that is, you would never attach one hydrogen to the bottom face and the second to the top face. When an alkyne encounters a palladium on carbon reduction, it doesn't actually stop at the alkene, but gets all the way reduced to the alkane. And so I've highlighted the first addition of hydrogen gas as blue, and the second addition of hydrogen gas as purple here. One thing to note, though, is that there is a way of reducing just partially, and that is using what's called Lindlar's catalyst. And this is a palladium-based catalyst, and we'll look at the structure in a moment. The thing to note is that when you start with an alkyne, you end up with an alkene that is Z, or cis. That is, the hydrogen gas has been added to the same side of this alkyne, just in the same way that it was added to the same side of the alkene. So Lindlar's catalyst, and I'm not going to ask that you remember this, you're simply able to write Lindlar's catalyst, is what's called a poisoned catalyst. And this is kind of a complex combination of palladium that's been attached to a calcium surface, some lead acetate, and this quinoline as well. And all these things together end up making it so the catalyst is not able to undergo this second catalytic reduction of the alkene to the alkane. Now, a cis double bond is great, but what about a trans? And sure enough, there's a reagent for that as well. In this case, you use metallic sodium, so this is like a chunk of sodium, dissolved in liquid ammonia. Liquid ammonia boils at negative 40 degrees Celsius, so this reaction is done at a very low temperature. Now, the hydrogen atoms actually come from the ammonia, so that this purple proton that's been highlighted here is where the protons come from for this particular reaction. So we've already talked a bit about how these reductions work on a metal surface, but let's look how this sodium metal reacts with ammonia to give you the trans product. Well, the first thing that happens is to notice that sodium has one electron, and it is relatively energetically favorable for it to donate that electron to something else to generate the Na plus ion. So we use the single-headed arrow electron arrow here. As this electron interacts with this triple bond, one of the pairs of electrons from this double bond has to move onto the carbon, otherwise there would be too many electrons on any given carbon. So you end up with this negative charge, and this radical species, the single electron, singly occupied orbital, was called a radical species over here. These electrons deprotonate the ammonia because they are significantly more basic than the ammonia, and as a result, you form sodium amide. So this is the same base that we actually have seen before. And this, again, now we have this product that has a single electron in this radical. There's more ammonia floating around in solution, and ammonia can donate another electron to now give you a full negative charge. And now that you have a full negative charge, you're going to simply deprotonate the ammonia to give you now the more stable trans alkene. I'm not going to ask that you know or memorize this particular mechanism, but it's interesting to see how metals can be dissolved and how they can give away single electrons at a time in the context of a reaction. Thank you for your time, and I look forward to your questions.